everyone. My name is Caroline Griffin. I am Riot's Director of Operations. You have found the Riot Lunch and Learn series, the place where we feature all of Riot's partners. I am super excited to have George with Chemi-Con here from Chemi-Con with us today, and Aparna from Aurora Group, who I will hand it over to in just 1 minute. A couple of quick reminders before we get started. Please keep yourself muted throughout the presentation. If you have any questions, please utilize the chat box, and Aparna and I will make sure all of your questions get answered. This meeting is being recorded and will be posted to Riot's YouTube channel, where you may find the recording later. We'll also post it on Riot's meetup page where you registered for this event. And the third reminder is the best way to view this presentation is in speaker view. That way you can get a nice big picture of the slides and then a picture of Aparna and George on the side. But without further ado, I'll hand it over to Aparna and George. Thank you for being with us today, y'all.
Thank you, Caroline. That was a wonderful introduction and reminder. We at the Aurora Group have been a supporter of the Riot for many years, and we appreciate all the good work you and your team do for our industry. As Caroline said, today's Lunch and Learn will feature United Chemi-Con capacitor manufacturer, also known as UCC. Before we get into the technical presentation, I wanted to tell you a bit about the Aurora Group. The Aurora Group is a manufacturer's representation firm with over 30 years of technical experience on electromechanical components for all kinds of applications. We are located in 5 geographic areas on the East Coast. Our particular group covers the Southeast. Our team is committed to facilitating electromechanical component solutions, and we do this by supporting engineers and our customers in a technical advisory role, as well as a supply liaison. We strive to assist and guide in solving technical challenges by offering the new and existing component solutions to engineers and their support team. Many of us on our team have experience or have technical engineering backgrounds. On our team in the Southeast, we have Bob, Ken, and myself covering the Carolinas, Bruce covering Tennessee, Alabama, and Mississippi, and Karen covering Georgia. And Kathy is our superb inside sales manager. Some of you may already know us. We support in the advisory role on a variety of components, ranging from magnetics, capacitors, of course, thermal solutions, connectors, touchscreen displays, frequency control products, capacitors I mentioned, and our applications we support in, of course, IoT, energy, telecom, military, aerospace, industrial, lighting, data centers, anywhere where electromechanical components could be used, electronics and mechanical components. Here's a quick glance at the manufacturers we currently represent. And we also participate in various trade shows and associations pre-COVID and during COVID. So hopefully we'll see you on one of the virtual events or the in-person events coming up soon, we hope. We also work with all distributor partners. So there may be somebody on here that you like to work with, and we work with all of them. In today's session, you will learn a bit about United Chemi-Con, get an overview of United Chemi-Con, Nippon Chemi-Con, get some information on comparison advantages among capacitor types, the electrolytic type, polymer capacitor type, and the polymer hybrid type, and of course, question and answers. Presenting the technical topic today is George Iftimie from United Chemi-Con. George is a graduate of DeVry University and joined UCC 20 years ago or so. He started in component engineering and has moved up to engineering manager. He has deep experience in capacitors and applications for capacitors, and his team supports North America, and he is located in the Chicago area. With that, I'm going to stop sharing and turn it over to George. So George, you can go ahead and share your screen.
As soon as I figure out how to do it. Here we go. Can you guys see the screen?
We can. Thank you, George.
Okay, I hope so. Well, thank you, Aparna, for the wonderful introduction. You're doing a much better job than I do it myself. But we are United Chemi-Con, Nippon Chemi-Con, depending on which part of the world that you're looking at. But United Chemi-Con, as Aparna mentioned, is essentially the America subsidiary of Nippon Chemi-Con. We are responsible for North, Central, and South America direct sales. We, in today's topic, I'll primarily talk about aluminum electrolytic capacitors and their, I guess if you want to call it cousins, the polymer electrolytic capacitors and the conductive polymer hybrids. We also make some ceramic capacitors, primarily higher voltage, higher capacitance, higher sludge sizes. We also make some high current choke coils, double layer caps or super capacitors, depending on how you call them, and then a relatively small lineup of metal oxide resistors. As Aparna mentioned, we are the leader of aluminum electrolytic capacitors. That includes the polymers and the hybrid that I mentioned earlier. We have roughly 30% or so of the market share, depending on which time of the year you look at. We tend to be vertically integrated, and the biggest reason for that is quality control. We found that it's difficult, much more difficult to control quality, especially for the key materials like foil, electrolyte, rubber bands, and so on. If we go to a third party, which supplies to multiple customers. We're also a big supplier of especially aluminum foil. We always supply etch foil, never formed. And the etching is basically what gives it the capacitance. The formation is what gives it the voltage rating of the part, and to a certain extent, the quality of the capacitor. We have roughly 40% of the market share for etch foil in the world. And we consume about 25% or so internally, and then we supply 15% or so to other competitors, if you want to call it that. We have worldwide manufacturing locations. We do have a factory in Lansing, North Carolina. If anybody wants to visit it, we're welcome to customer visits. Maybe not so much right now with COVID going on, but generally speaking, we are. That factory primarily makes large size capacitors, larger size snap-ins and screw type capacitors. But we also have factories in Japan. Japan, obviously, we are a Japanese company, so Japan is our primary base of operations. We have 4 or 5 factories in Japan. And we have a factory in Indonesia, 2 of them in China, 1 Malaysia, and 2 factories actually in Taiwan. I mentioned earlier about raw materials. And raw materials, especially the rubber seal, the foil, and the electrolyte are really the primary drivers of quality and long-term reliability. We are, if not the only one of the handful of suppliers that actually mix their own electrolyte. We buy the raw ingredients and then we mix it on site. And electrolyte tends to be tend to absorb water, tend to be very hydrophobic. So it's very, very important to consume the electrolyte within typically 2 or 3 days after it's mixed. Otherwise, it will start to basically degrade unless it's impregnated inside the element. I mentioned a little bit about the aluminum foil. Foil is basically they're called aluminum electrolytic capacitors. That's what gives the capacitance. The etching gives the capacitance, and you have the formation, which actually provides the voltage rating of the capacitor itself. I could talk for hours about the foil and the electrolyte. And then, of course, you have the rubber band. Most people think of the rubber band as just being a plug. The rubber band's main purpose is to maintain seal integrity. And this is primarily true for liquid electrolytic capacitors, but also to a certain extent for polymers, and especially also for hybrids. You have a limited amount of electrolyte inside the capacitor. If you don't control the electrolyte consumption and diffusion, you are going to have a very short life and a very uneven life. So especially when you're talking about long life, high temperature capacitors, the rubber band is really the key to the long-term performance of that capacitor. We tend to make a lot of our assembly machines also, as you see on the right slide. It's cleanliness is very important. We always joke that you can eat off the floor in most of our factories. I wouldn't recommend it, but it is very, very important to keep it clean. It's not a clean room facility like it is for a semiconductor type of product, but it is very, very important to have good cleaning. And going back into the main topic of the presentation today, and I should have mentioned earlier a little bit, I tend to run a very open presentation. Obviously, we can wait until the end for any questions, but if you have any questions in the middle at any time, feel free to interrupt basically and ask. The three capacitors are essentially, I call them cousins. You have the aluminum electrolytic, you have the polymer, and then you have the polymer hybrid. Especially on the polymer and the polymer hybrids, they are really complementing each other. The polymers are really efficient at, and you'll see from the next slides, at low voltage, up to perhaps 25, 35 volts. And then once you go beyond that voltage, then the polymer hybrids are basically the best option. The aluminum electrolytics, and they all have their own advantages, they all have disadvantages. Sometimes it's a matter of cost and volume available. It is important to know their strengths and weaknesses in order to choose the best type. It is rarely simple where you can take a polymer or a hybrid and replace aluminum electrolytic capacitor. There are always drawbacks, or there are always complications basically when you try to do that.
Hey, George, we have a question. You're probably going to get to it right now, but just point out the significant differences in construction for supercapacitors, ultracapacitors, and compared to the much lower capacitance devices. Maybe, wherever that topic can fit in.
Well, supercapacitors are a totally different breed. They have essentially a different electrolyte, different foil. And this, I'll use this slide actually to explain the differences too. So I'll talk about the liquid, hybrid, and solid polymers, and then I'll mention the supercapacitors in a little bit. But essentially, a capacitor, and I had some extra slides for normal construction of capacitors, but I'm sure everybody knows exactly what, how they are built and so on. But essentially, you have an anode foil, a cathode foil, and you have a separator, and then you have the liquid in the middle. And the separator's purpose changes depending on the type of capacitor you have. On a polymer capacitor, the separator is there to purely to prevent the two foils from touching each other. It is typically a plastic-like material. It doesn't serve any other purpose except to just prevent the contact from the two. When you're talking about a liquid type of capacitor or a hybrid capacitor, the separator provides the storage area for the liquid electrolyte. So of course, it has to be able to prevent physical contact between the two foils, but it also has to be able to hold the electrolyte and allow migration of the electrolyte from the separator to the surface of the foil. In liquid capacitors and hybrid capacitors, almost 100% of the liquid electrolyte is inside the separator. If you open up an electrolytic capacitor, there is no free liquid that you will find in there. It is not like a liquid, like an oil-filled film capacitor. It'll be almost dry once you open it, once you take it apart. The hybrid capacitor is really what it is. It is a hybrid between a polymer and a liquid. So it starts life as a conductive polymer, and then it has a secondary impregnation where we add the electrolyte. And the liquid electrolyte's main purpose is to protect the polymer material. The polymer material is very sensitive to humidity, and that makes humidity applications, like outdoor applications or automotive applications, problematic for full polymer capacitors. And this sensitivity and the drawbacks and the side effects of that increase almost exponentially as the voltage rating of the part increases. On the DL caps or supercapacitors, the construction is basically the same. The difference is the electrolyte is different, and we use what you call a PC electrolyte, polypropyl carbonate electrolyte. We don't use acetonitrile electrolyte for our supercapacitors. Acetonitrile has a very low boiling point and flash point. And then the second part is when it does combust or vent, it has a tendency to create cyanide, especially when it burns. So we use PC, what we call PC electrolyte, which has a slightly higher ESR, especially low temperatures. And then also it typically has one of the foils, especially one of the foils of the supercapacitor is typically carbon. It typically has an aluminum foil and then a carbon foil. And that's where you get the very high capacitance. If you'd like more information, we have more presentations for supercapacitors and why they are unique and so on. Is that good enough?
Yeah, that's good, George.
So, as I mentioned briefly before, the most important difference is basically the electrolyte type. And the electrolyte type will determine or force changes to the foil and the paper. And of course, the electrolyte itself plays a major role in the capacitor and how the capacitor behaves over life and how the capacitor behaves over temperature. One rule of thumb a little bit is that as the voltage increases on the capacitor, the electrolyte gets thicker and thicker. The other kind of like truth about capacitors a little bit is that if as a liquid, the liquid is affected by temperature, especially for the electrolytic capacitors. And a thinner electrolyte typically has a lower ESR versus a thicker electrolyte. But a thinner electrolyte is also more reactive, and it also tends to evaporate sooner. So there's always a trade-off or a catching game or a trade-off between ESR and life. If you want a low ESR capacitor, you typically have to sacrifice life or endurance because that electrolyte will just simply evaporate faster. And most people think electrolyte is lost through diffusion in an electrolytic capacitor especially, but that's not necessarily true. Most electrolyte is actually consumed by the capacitor to heal damage to the oxide layer. Some of the components, especially hydrogen, will eventually escape through the rubber band, but the active portion of the electrolyte is basically used to create additional aluminum oxide. This is a kind of a little chart on where the hybrid capacitor and the conductive polymers are. And you'll see them there. The conductive polymers and the hybrids are essentially on top of each other. It's just different voltage. And then you have the aluminum capacitors, which are sort of on a class of their own. A little bit on the voltage. Hybrids are usually, available up to 80 volts. Some competitors have higher voltage than that. But we found that we're working on a 100 volt rated voltage polymer, but humidity resistance is much lower for 80 volts than it is for 80 volts and below. And then there's some points of ESR and so on. Electrolytic capacitors are, of course, available all the way up to 800 volts. And we're trying to make them even higher than that. But the most cost-effective for liquid electrolytic capacitors is roughly 650 volts. Once you exceed that, ESR of the 700 volts and above capacitors is very, very high due to the internal arcing that will happen inside the capacitor itself. Aluminum electrolytic capacitors, I mentioned earlier a little bit. So essentially, you have a cathode foil, an anode foil, and a separator wound together. This particular model is a radial capacitor, a through-hole capacitor. The only real difference between different types is construction packaging. Surface mount will have the two terminals basically bent at 90 degrees, and obviously they'll be flatter. The snap-in will have a series of foldable tabs between the element and the terminals. All of these have drawbacks depending or side effects depending on the application, especially mechanical and vibration. The radial through-hole part typically tends to handle vibration the best, with the screw capacitor being one of the worst ones in terms of vibration. And that, there is things we can do to capacitors to make them more resistant to vibration if we know that vibration is going to be a concern in the application. A lot of times when customers get in trouble with vibration failures is because they didn't tell us that they didn't provide enough details on the application itself. Again, this is just a way to connect the tabs. So you have the anode foil, which is of course a positive electrolyte. This is basically where the bulk of, where a lot of your capacitance is coming from. It's a very highly edged surface, and then you have the aluminum oxide. Electrolyte is really the true cathode, not really the cathode material. You have to be careful with electrolytic capacitors, especially on the snap-ins and screw capacitors, on electrically separating the can from anything that's electric conductive in the circuit itself. In a lot of capacitors, especially the newer higher ripple current capacitors, the can is mechanically connected to the cathode of the capacitor. So any type of connection will cause problems. But even on normal electrolytic capacitors, there is a variable resistance between the cathode terminal and the can. So if you have contact, you will eventually have problems, especially as the temperatures warm up in there. Separator is basically a piece of paper, and there's to simplify things, it acts as a storage area for the electrolyte primarily. And then you have the cathode foil. Some of the strong points or advantages: they have wide voltage range and very high voltage availability, 800 volts and soon to be higher. Very high capacitance. They have a self-healing function, a very good self-healing function. Hybrids also have it. Polymers technically should have it, but basically what we mean by self-healing is the aluminum oxide gets damaged during application, and it gets damaged by ripple current, temperature, and in various factors. So if you don't do anything about it, you will eventually have a ever decreasing voltage thickness, or a thickness of the aluminum oxide, and a lower voltage, quote unquote, resistance of that aluminum oxide. Self-healing will essentially form new aluminum oxide to heal the cracks. In order to build aluminum oxide, of course, aluminum oxide is just aluminum and oxygen. Aluminum is obviously, the foil is made of aluminum, so that's easily present. The oxygen is a little bit more difficult to obtain, especially in a polymer capacitor. So polymers, and I'll mention earlier a little bit in a presentation, polymers have a healing function, but it is very, very slow. With aluminums and hybrids to a big extent, if you have an overstress condition and the capacitor didn't fail catastrophically, then essentially you can assume that it healed correctly and you don't have to worry about cumulative type of stresses. With a polymer capacitor, you do have to worry about that. Capacitance, of course, doesn't vary with applied voltage, and that's true for all the capacitors I'm going to mention today. They are, cost and volume efficient. I'm not saying cheap. I hate to use the word cheap, but cost effective, basically. And then you have a wide range of size available, from a 4x5mm surface mount all the way up to 100mm by 270mm lengths type capacitor. And of course, pretty much any voltage, any capacitor that you can think in the middle. And of course, you have different types of constructions available. You can technically have a large size snap-in or a hybrid or a large size polymer, but typically cost is not very efficient. And the other issue that we run, especially with polymers, is the capability of the packaging to carry the current rating of the element itself. We may have an element that has a 2 or 3 milliohm ESR for capability, and on paper it should be able to handle 80, 90 amps of ripple current. However, we cannot get a packaging that's capable of transferring all the current. So you'll see this is the main reason why polymers tend to be size limited. Another strong point, leakage current is very, very low and it's very, very stable, at least for our capacitors. I've seen data for some competitors, which is not so good. But then that's very important. You know, you want the consistent performance of the capacitor. And of course, leakage current is what consumes the electrolyte. So having high leakage current will almost always translate into a short life. High temperature ratings. And that right now we can offer up to 150 degrees C rated electrolytic capacitors. 1,000 hours right now, 2,000 hours will be very shortly. They have a very good self-healing function, which I mentioned with earlier. And they are pretty much, I don't want to say immune, but they have a high resistance to voltage and current surges. As long as they're not repetitive, especially on the current, you don't really have to worry about it. You don't have to worry about inrush current. You don't have to worry about a sudden voltage decrease or sudden voltage drop. There are, of course, limits to this. And if it's a repeating type of event or really outside of its normal rating envelope, we'd like to know about it. But for the most part, it is rarely an issue with aluminum electrolytic capacitors. Weak points of aluminum electrolytics. Of course, you have a finite amount of liquid electrolyte. You will consume that as a part goes through its life, and you're going to have a limited life because of that. Because you have a liquid electrolyte, you tend to have a higher ESR high frequency, and you tend to have a higher ESR at low temperature. I mentioned earlier about the electrolyte. The electrolyte's viscosity changes with temperature. And as the temperature decreases, the electrolyte gets thicker and its ESR basic or resistance increases, which translates into higher ESR and lower capacitance. You tend to have a lower frequency ceiling compared to a polymer and a hybrid. And that's basically the self-resonant frequency tends to be lower than the other type of products. You have a significantly lower ripple current rating. And some of that is due to its higher ESR, and some of that is to do with the fact that it has to be, you have a certain life target they're trying to meet. So having a higher ripple current rating will translate into more internal heating and a shorter life. And I mentioned earlier a little bit about the low temperature performance, which is not a defect, but it is something to keep in mind. I've seen a lot of design issues with customers where they didn't take the low temperature performance into account. They assume that whatever happens on a bench will continue. And of course, it doesn't happen, especially at very low temperature, below -40 degrees C. On some capacitors, especially high voltage, you can lose over half of your capacitance, and your ESR could be 4 or 5 times higher at those temperatures. It is transient. It will not damage the capacitor. But essentially, it's at low enough temperature, you're going to have a block of ice. You know, you're really not going to have a capacitor there anymore.
So George, we have a couple questions. So one directly has to do with a note that you mentioned earlier regarding screw terminal capacitors. Said that tend to handle vibration more poorly than others.
Yes.
But in light EV applications, so electric vehicle applications, tend to use these screw-in terminals for high capacitance in the sub 80 volts. The question is, should we create small mounting boards and solder connect instead? These are related to the vibration question on screw-in terminal capacitors.
Well, I mean, it's a picture is worth 1,000 words, and I mean, I can try to find a picture quickly about it. But if you imagine the capacitor, you have and snapping and screw capacitors are essentially built the same. And by snapping, I mean the little curved terminal type of parts. The difference is just the outside, but internally you have an element, and I'll go back to this page. Well, here, you can go back to the picture. But internally, so in this picture, you have a direct connection between the terminals and the element. So essentially, when you mount the capacitor on the board, you lock the lead wires into place, and then the only movement possible will be on the top of the capacitor. But you don't have a unibody. You have two individual components moving at different frequencies. So what tends to happen during vibration with electrolytic capacitors is that you have, if you imagine a side-to-side movement, the outside body will move to the left, for example, and then the vibration limit is or the movement is reached, the movement limit is reached, and then it will start moving in the opposite direction. Well, the problem is that the element still wants to move in that direction. It's kind of like a crash dummy. So you have a lot of resonance, basically, a lot of internal damage between the element itself hitting the can. On a radial type component, the only movement is going to be on the top. On a snap-in or screw capacitor, you have essentially a floating element. The element is not directly connected to the cover. So from the advantage of that, of course, is that you can apply a lot of mechanical stress to the cover and it will not translate into any damage or stress to the element itself. The downside is that now you can have movement in both the top and the bottom of the element. And of course, when you couple the fact couple this with the fact that snap-ins and screw capacitors are larger in size, they have a bigger mass to begin with, the problem gets progressively worse. Now, that being said, there are things we can do to alleviate the problem. Especially on screw capacitors, a lot of our capacitors we can offer with what you call dimples, essentially dents. So if you look at this little gap between the yellow element and the outside can, we crush the can to mechanically lock the element in place. That construction is, I don't want to say indestructible, but it's very difficult to have any vibration problems if you have that type of capacitor. We can also do that with certain snap-ins. And on the ones we cannot do, we have some other methods we can do, we use to increase the resistance to vibration. But everything really relies on us knowing the details of where the part is going to be used and what the vibration or expected vibration conditions are going to be. We typically don't offer enhanced vibration designs from the start. One, there is a cost associated with that for the most part. And second, sometimes there is a capacitance decrease also because of that, if you have dimples especially. So, but there are things, it depends a little bit on, are they more sensitive are screw capacitors and snap-ins more sensitive to vibration than radial capacitors? And the answer is certainly yes. You can have them fail, especially when you're talking about high frequency vibration at sometimes 100 hertz, 120 hertz. You can cause a aluminum electrolytic screw capacitor to fail. But it depends on, there's a lot of details that are very application or mounting specific. You may have the same capacitor, same exact design, pass in one application and fail in another application because it's mounted a slightly different way. And the same is true for board mount components also. If you have there's always a danger sometimes when you try to put a whole bunch of capacitors in close proximity on a PCB, that you're adding a lot of mass. So if you don't support that PCB well, the whole board will actually flex up and down. So you're going to have a lot of resonance vibration that you perhaps didn't expect beforehand. And then you're also talking about heat and some other components in there also. But so again, going back, our screw capacitors and especially snap-in used in electric vehicles, yes, especially on the onboard chargers and so on. Are customers using standard design or vibration enhanced designs? It depends on the customer. Some are, some aren't. And it depends a lot on how the capacitor is, where that unit is mounted in the car, and to a certain extent, the type of car. I would like, you could always make the argument that a Lincoln rides softer than a Toyota Corolla. So if it's softer for the path for the driver, it's going to be softer for any electronics inside the car. So that makes a little bit of a difference too. I'm not sure if that answered the question, but again,
yeah, it answered the question. Good job, George. There's another question that's come up about more of the low voltage capacitors in a solar application. And I think you might be getting to some of the other two capacitors where this question might fit in better. So here's the question. Common use of electrolytic capacitors for decoupling between the solar panel and the IoT device. These are for low voltage applications, 6 to 12 volts typically, and they only need 100 to 1,000 microfarads. What would be the best capacitor for this technology for this use case?
It depends on the expected life, but probably liquid electrolytic capacitors, I would think. It's mostly because, I mean, you basically can't really, or you don't necessarily have to use hybrids, you know, and you can certainly use a polymer, but the issue a little bit is also polymers tend to operate best at high frequency applications. You know, they're not worse, and I'll mention that in a little bit. They don't perform worse than liquid electrolytic parts in low frequency applications, but they don't perform any better either. So you have essentially it's not the best tool for the job necessarily, unless you need the advantages of the polymers. You know, they're always going to have a flat temperature performance. They're always going to have a very long life compared to a liquid part. So I'll go back to the question. I mean, if you didn't answer it, you know, you can ask again, and then we can go back to that in a little bit.
Yeah.
But
yeah, we got, let's see, another 25 minutes, and you want to leave a little bit of time for questions at the end. So we'll just speed through.
Okay, give me 5 seconds, please. My battery is running low.
So while we're waiting for George to reconnect his computer with his power source, anybody has any other questions, feel free to ask them in here. And if you don't get an answer, we'll circle back around with you later to get you an answer.
Perna, what is the best way for those on here, if they think of a question later, to reach you?
I've actually, well, the best is to use my email, of course, and I can send my email, which is, everything's by email these days. Here's my email. So I just put it in the chat box. Everybody's got it.
Thank you, Perna.
Yep. George, your presentation went offline, so you know. I think George went offline.
Yeah, I think he might have gotten kicked. I think maybe his, oh, there he is. He's back.
Okay.
Sorry.
No worries.
Do not know what happened.
So go ahead and reshare your screen.
Let's go back. Okay.
Yep. No problem.
Are we back?
Yep.
Okay.
Yes.
All right. So polymers. That was unexpected.
Yeah. Well, you can go ahead and put it in presentation mode so it's bigger.
Yes.
Yeah.
Here we go. So sorry about that. So polymer capacitors, I mentioned a little bit earlier. Essentially, it's similar to an electrolytic, except you have a polymer material or a two-part monomer that actually coats the surface of the aluminum foil. The separator is essentially just a piece of plastic that actually holds it in place. The advantage, of course, one advantage is that the solid electrolyte functions by electrical conduction, which is very fast, and the liquid electrolyte is ionic conduction, which is much slower and temperature dependent. It's the same thing, that I mentioned earlier a little bit. Some of the advantages, It has a, most of them are due to its solid electrolyte. It stays solid. So it has a very low ESR, especially at high frequencies. It has a very high ripple current, primarily because of the low ESR. It has a essentially flat behavior over temperatures. So when you're talking about designing a capacitor, essentially whatever you see at room temperature, you will see at -55, or you'll see at +125 degrees Celsius. Same as electrolytic, capacitance doesn't change with the applied voltage in any way. Operating frequency range is solid. It has a very low ESR, so it's going to have, for the most part, a very high resonant frequency. It's not uncommon to see them operate well over 500 kilohertz or even megahertz, especially on the small size parts. It has stable characteristics over life. It doesn't really degrade over life. There is a limited lifetime for polymers also, but it is significantly longer than electrolytic capacitors. And I mentioned earlier a little bit, it's easier to design and simulate because you don't really have to worry about the temperature behavior of that capacitor. Disadvantages: it has a higher cost, of course, but this higher cost is really an issue only if you try to replace one-to-one. So if you have a 10 by 10 millimeter size electrolytic and you're trying to put a 10 by 10 millimeter size polymer, of course the polymer is going to cost more. But generally speaking, you don't do that. You would replace 5 or 6 electrolytics or a larger size electrolytics with one single polymer. Leakage current is one big issue that polymers have. It is significantly higher, usually it's 3 to 4 times higher than a electrolytic capacitor or a hybrid, even a steady state. And it can also be unstable or variable. The disadvantage, when you have a stress, an electrical stress, ripple current or voltage on a electrolytic capacitor, you'll see that represented by a spike in the leakage current. And this is why we refer to the leakage DCL value as kind of like a snapshot into the health of the oxide layer. A poor degraded oxide will invariably have a higher leakage current value. When on a liquid part or a hybrid, any spike in any damage to the oxide layer will tend to be repaired very quickly. On a polymer, it may take significantly longer. Something that will take seconds on a hybrid may take hours on a polymer to heal. So you do have to worry about cumulative type of damage effects. You're kind of like chipping away over and over again until eventually you may have a problem. Voltage range is limited to 35 volts. Again, that's primarily a design issue due to the polymer's weakness to humidity. We can have higher voltage polymers and they are available, but they are so weak to humidity that it's not really worth designing capacitors at the voltages. And then goes back with the next one with sensitivity to humidity. And then the other problem is that when polymers fail, they almost always fail as a short circuit, especially when you're talking about a higher voltage. The low voltage capacitors, by the way, the reason why they don't fail as a short circuit is because you have enough physical separation between the anode and cathode foils to prevent arching. Basically, it's not that the polymer doesn't degrade, it's the fact that you just physically, the two foils are too far apart to arch at low voltages. I mentioned the slow healing, and in terms of low frequency, and I'll show you a couple of graphs in a little bit on the reason why. ESR at low frequencies is very high. So if you have and this is also part of the reason why you don't see higher voltage polymers, is because on the input side, you typically don't want, you wouldn't want to use a polymer even if it is available. Any questions for the polymers?
No questions on polymers.
Hybrids, hybrids are not new per se. I mean, we've been operating hybrids for well over 5 years. It's something that's always been around. They really are supplementing polymers. So for the very low voltage, up to 16 volts or so, you typically would use a polymer. And then beyond that, higher voltages than that, you would use a hybrid capacitor. And it's kind of really the best of both worlds a little bit. Is that, so essentially a hybrid is a polymer capacitor where you take away, you replace the plastic separator with a paper separator, and you add a little bit of electrolyte in there. And I mentioned earlier, the biggest function for that liquid is to protect the polymer from humidity, basically. This is basically the same. The only difference that you have the electrolyte difference. And of course, there's a combination, there's a lot of variables on hybrids. You know, the playing with a ratio between obviously the type of polymer and the type of liquid electrolyte will make a big difference on what the part performs. Also, playing with a ratio between the polymer and electrolyte will change how the part behaves. If you have more polymer and less liquid, you're going to have a quote unquote better part electrically. You're going to have a lower ESR, longer type of part, higher ripple current. But then the downside is that it's going to be weaker to humidity because you have less electrolyte, which will eventually evaporate. The advantages of the polymers: they have a very low ESR, high frequencies, not quite as low as full polymers, but very close. They have a very high ripple current also because of the low ESR. They also tend to have a very stable ESR over temperature, same as the polymers. The polymer material is what actually drives or controls ESR. But because they have the liquid electrolyte also, they will have a capacitance change over the temperature. Of course, the capacitance does not change with the applied voltage, and they also have a low and stable DCL. Not quite as low as a liquid capacitor, but very low, but much lower than a polymer capacitor. Frequency range, of course, is very high, 300 kilohertz and above. They have a very high humidity resistance. They have a long expected life, of course, especially when you take into account the fact that the ripple current is significantly higher than an electrolytic capacitor. They will almost invariably, I mean, always is a dangerous word to use again. You know, assuming that it's not severely overstressed, the failure mode will be open circuit. So it will dry out essentially like an electrolytic capacitor versus failing as a short circuit like a polymer, which is an expected failure mode. And they have a very wide operating temperature, -55 to +150 degrees C. Disadvantage of weak points: it's limited basically up to 80 volts, 16 to 80 volts or so for now. Capacitance values are limited by the narrow size available. The biggest size available is 10 by 16 millimeters. So invariably, because of that, you're going to have a significant lower capacitance. Technically speaking, we can make higher capacitance versions or larger size versions for hybrids also. Same is true for polymers. But the market need is not really there when you take into account the voltage range. You know, most common reason why customers switch from liquid parts to hybrid or polymers is because they're trying to decrease the number of capacitors used in a particular bank. So ripple current, ESR, is typically the driving factor. And because the hybrids or polymers have such a low ESR and such a high ripple current, the number of capacitors and the total capacitance also comes along with it. So there's really no need for a 2200 microfarad 18 millimeter by 40 millimeter hybrid capacitor, for example. At least not yet. But it is certainly possible from a manufacturing standpoint if that were to be the case. Cost, of course, is higher than a liquid type, and of course part of the reason is the production. I mean, essentially, initially hybrids actually cost more than polymers. You know, you kind of have to build, from a manufacturing standpoint, you have to build a polymer and then actually add another couple of steps to make it into a hybrid. Again, it's not all suited, same as the polymers, for low frequency operation. And then you have a capacitance that does change over life and it does change over temperature. And you'll see some of the data here. This is essentially a very similar capacitor. So if you look at the bottom, the red and the blue, this is ESR basically. And you'll see that the polymers and the hybrids, the bottom curves, are essentially very similar in terms of ESR. And of course, liquid electrolytic capacitors, they are an order of magnitude higher basically than the hybrids and the polymers. And this is typical behavior. The only thing that's going to really change is the low point, and a little bit of distribution depending on what size you're looking at. Temperature characteristics, again, if you look at the electrolytic capacitor and then you look at the hybrid capacitor, especially on the ESR, if you look on the bottom side, you see that once the temperature decreases below, especially below 0, you'll see the ESR of the electrolytic capacitor really skyrocket. I mean, it goes up significantly versus a polymer or hybrid, which essentially stay the same. This is another example, a little bit of a especially, and you'll see one thing to see over here is, especially at minus 20 degrees C, the difference is significant, you know, and one other thing that you see on the application itself, of course, there is no difference in the voltage, in a peak voltage on the hybrid capacitor. You know, it doesn't matter that it's 25 degrees or minus 20 degrees C, essentially you have the same exact behavior. But with a liquid part, you have significantly worse change. And that's before you even take into account the fact that you're only looking at 1 hybrid versus 10 electrolytic capacitors. This is endurance test. And again, what you see, I mean, and I mentioned earlier a little bit, a polymer capacitor is basically flat. There, if you look at the blue line, you know, capacitance, ESR, essentially whatever you started with, you're going to end with. On a hybrid, a liquid part, you know, essentially you're looking at, you know, 30% change or so after 4,000 hours. And then you have a hybrid part, which is a little bit in the middle. Capacitance, of course, is going to be almost in the middle. The ESR actually does not change as much, especially compared to an electrolytic. One thing to keep in mind here is that the electrolytic couldn't even survive 4,000 hours before it went out of spec. Any questions to that?
Yeah, no questions yet.
Okay. Now, a little bit of a kind of like a roadmap on, and this is primarily for hybrid capacitors. I mean, if anybody has any questions about other type of components, please let me know. But there is, you know, the trend here is, especially for hybrids, is, I mean, I guess it's true for almost any type of capacitor, is higher capacitance and higher temperatures. Higher capacitance is more miniaturization and so on. And then you have the higher ripple current that comes along with it. And most of the demand is surface mounts, just because of ease of mounting and so on and sizes. We do see some demand for radial components also, especially in the telecom world. Ajax F series is our high ripple current part. And keep in mind, as a comparison, Ajax E is only 2 years old. So you want, you know, in less than 2 years, actually, the ripple current goes from 2.9 amps all the way up to 3.9 amps on a single capacitor and an 8 by 10 millimeter size. To put it in perspective, an electrolytic capacitor, a liquid electrolytic capacitor, the best ripple current you can get is roughly 800 milliamps in that size. So you go from 800 milliamps all the way to 3.9 amps. And this part should be available. Samples are available right now. Mass production should be sometime in December, November, December timeframe. And these are very, very small sizes. Now, if you look at a true polymer, you know, when you're looking at another amp or amp and a half or so of ripple current on top of this value, but not at 35 volts. It will be limited to 16 volts and below. This is kind of like a little table. Then some of this information is also available on our website if needed. Ajax J is essentially a miniaturization version. So we keep the same ripple current ESR as a current Ajax J, and then we increase the capacitance further. Ajax J hybrids still have a capacitance, quote unquote, deficit per size and voltage compared to electrolytic capacitors and polymer capacitors. And some of that has to do with the fact that the design margin are a little different. And then some of it has to do with the fact that you know, it's just the nature of the miniaturization, basically. But to go from 47 microfarads to 82 microfarads is a significant increase. The next thing that I'm going to talk about, and there's only a couple more slides, is a new type of process that we're having. In this slide is for hybrids. We also are planning to offer it for liquid electrolytic capacitors. And it's a two-pronged reason for that. One is, of course, higher life, longer life. We mentioned earlier about the electrolyte actually diffusing through the rubber band and electrolyte being quote unquote lost a little bit. And I mentioned that most of it is consumed, but some of it is actually lost through diffusion, especially on thin rubber band designs like surface mount. So anything we can do to control or decrease this amount of electrolyte diffusion will result in a longer life. And that's essentially what this thin layer of epoxy does. It essentially allows us to decrease the evaporation rate and basically push back the end of life. The other advantage is that vibration resistance is significantly improved. One big issue with most failures for surface mounts occurs right where the purple layer is, where that electrolyte is. Essentially, you have a capacitor that actually goes side to side, and you're going to break the terminals right where they come off the pad, essentially at the 90-degree bend. And we found, of course, we have the high vibration pads available on the parts, and that makes a big difference. But this option should be less cost effective. More cost effective than the high vibration pads. And they also don't require a different pad layout like the current high vibration option that we have. But even on this capacitor, for an endurance standpoint, we're looking at 8,000 hours of endurance up from 4,000 hours. So double the endurance without any change internally on the capacitor itself. The only change on the capacitor is that epoxy layer. And of course, we are, the polymers is also something that we're looking at, where we can perhaps control or minimize the amount of humidity intrusion into that element. I mentioned earlier, I didn't mention earlier, but part of the reason why polymers are more sensitive to humidity is really the construction type. Electrolytic capacitors have a liquid, and hybrids have a liquid electrolyte inside. So what that means really is when you operate the capacitor, you operate at a slight internal pressure difference between the interior and the outside. You will evaporate a little bit of electrolyte and you'll raise that internal pressure. The effect of that is that you essentially control any contaminants from the outside, because you're making yourself an air curtain. Pressure is higher inside than outside. So that things basically that outside stay outside. A polymer has no liquid. So a polymer, regardless of what temperature or how hot you're running that capacitor, will always have the same pressure as the outside. So it is much easier for any contaminants that are external to actually enter the capacitor and basically cause degradation on the capacitor. With electrolytic or hybrids, you really only worry about that when the unit is not operating.
Thank you, George. I have one last thought. It looks like, from what you're saying, that United Chemi-Con is really going further in development for hybrid capacitors because of some of the inherent advantages. Would you say that's true as you're showing this?
Well, we are developing all three type capacitors, and keep in mind that they are similar to each other more than they are different from each other. So a lot of materials are used across the capacitor board. Foil, for example, foil is foil. Essentially, we use the same foil. If you pick a given voltage on a capacitor, we would use the same exact foil on a hybrid, electrolytic, or polymer, regardless of what kind of construction it is. Some of the electrolytes are very different. The electrolyte we use in a lot of hybrids is really similar to the electrolyte we use in high temperature electrolytic capacitors.
Got it.
So you look at that accent too. Same is true for supercaps, the DL cap that we use. The electrolyte we use for supercaps is 90% similar to what we use in some low impedance electrolytic capacitor parts also. So there's a lot of cross movement between materials, and even this mold that I mentioned earlier. Of course, we are putting a lot of effort and a lot of R&D effort into hybrid capacitors, mostly because, at least in North America, almost 90% of the market is automotive, and they can be very demanding. And of course, they move very, 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 very fast. And with all of these safety features and everything being introduced in cars, the hybrids are really the perfect type of capacitor for those applications. If you move farther and farther out to the periphery of the car or the perimeter of the car, vibration and temperature extremes become more and more severe, mechanical shock and so on, especially when you move to sensors and so on, mirror sensors and so on. So that's kind of, it may look like we are ignoring some of the other type of capacitors, but it's not true. It's just these are kind of the front and center of what customers are wanting and what we're offering. And our development tends to be a little cyclical too. But of course, this presentation is mostly about hybrids and polymers. I mean, we do have radial components and so on. And electrolytics for liquid parts, the bulk of the new products are high temperature and high voltage. So most of the new products introduced in the liquid field are going to be 135, 125 degrees C type of components, 150 degree, and the high voltage, 500 volts, radials, and so on. And of course, some of it has to be with automotive, but to put things in perspective, Nippon Chemi-Con's group direct automotive business is 25% of our business is that. And that's when you look at that volume, which is 1.1 or so billion dollars a year. So almost $300 million a year is direct automotive. And you probably have another 10 or so % of that of business that's indirect automotive. Not everything is, direct is directly to basically tier ones and OEMs. But there's a lot of business that it's kind of difficult sometimes to really figure out where it's going. Telecom is a big market for, especially for United Chemi-Con for North America.
Well, thank you, George. I really appreciate it. And like you said, the electric vehicle and vehicles are pretty hot right now. So everybody's got that eye on those technologies, as well as 5G, solar, and anything to do with energy as well. So really appreciate it. If anybody has any questions further, we can answer them later via email. After this session, we'll send out the full presentation as well as the video. And I'd like to turn it back over to Caroline to close us out. Thank you so much.
Thanks so much, Aparna. As always, wonderful job with the questions. Really appreciate your support. George, thank you so much for a very informative presentation. As Aparna mentioned, this was recorded, will be posted right to YouTube channel and then sent out to you all. As always, thanks for being with us. Stay safe, stay well, take care, everybody.
Okay, thank you.
Thank you.